Hello everyone. This is a video for section 6.2 where we're talking about the binomial probability distribution. You know, in 6.1 the topic of interest is simply discrete probability distribution, or a probability distribution where you've got a discrete variable. We're still interested in that case, the discrete variable case, so we're thinking getting whole numbers as possible data values. But this one, binomial, this is a classification that is a lot of the common kinds of situations that we would encounter in probability questions. Binomial, all that it means is that you see in the definition here, it's a discrete probability distribution, so that's what we've been dealing with, that describes probabilities when there are two. We've got some specific jargon here called mutually exclusive. If you remember what that means, that these two outcomes, they can't happen at the same time. And there are two of them, so that's the bi part of binomial. There are two possible outcomes in a binomial probability distribution. There are two possible outcomes for the variable. These ones sometimes are called success and failure. But many common examples, I'm thinking flipping a coin. This would be a binomial kind of situation, because you know that whenever you flip a coin, there are two possible outcomes, which is heads and tails. And you can see how these could be rebranded as success and failure in the case that we're doing maybe a drug trial. If you can imagine the way that an experiment could be done for a drug trial, if you're testing this drug, if it's going to cure some sort of a symptom, then you're going to have people that have that symptom, and then you're going to give them the drug and see, did it work or did it not work? And so that would be the two mutually exclusive outcomes. Either the drug worked or it did not work. And there are 4 specific criteria, but these ones, they can be a little bit technical, and most of the time they don't help us decide if we're dealing with a binomial probability experiment as much as just looking for these two that are super important. For each trial, there are 2 outcomes. And also, the experiment is performed a fixed number of times. And so what this would be, if we're going to make a binomial experiment, and we're going to be doing the flipping a coin sort of an experiment, then we have to say ahead of time how many times we're going to flip the coin. So say if we're just going to flip the coin once, that would be a binomial probability experiment, would just be flipping a coin and seeing whether you got heads or tails. And if you think about making a probability distribution for this, making the table like we did in 6.1, we're going to flip a coin and see, did we get heads or tails? And we could count. Say if we're just going to count the number of heads that we get, that can be X. This is the number of heads from flipping a coin one time. Well, how many different values could we get for X? If you flip the coin, either you could get heads, in which case you got 1 heads, or you could get tails, in which case you got no heads on that flip. And this one, we should put what is the probability to get these different values of our random variable. The probability not to get heads is 50%. The probability to get heads is 50%. And this here, we see this is a binomial distribution because we're dealing with a discrete probability distribution where there's 2 possible outcomes, either getting heads or not getting heads. And then something else to point out in these criteria is that the trials are supposed to be independent. That means the probability of one trial does not affect the probability of any other trials. And if you're just repeatedly flipping a coin, let's say our experiment was to flip the coin more than once, maybe twice, we could draw a distribution for that one. But those trials would be independent of each other, because if you flip a coin and you get heads, it has nothing to do with the probability to get heads on your next flip. It's still going to be 50-50. And that also is sort of the same criteria as number 4, which is that the probability of success is supposed to be the same for each trial. This is generally achieved by the independence factor. There could be something else going on making the probability change each time, but that would be something to look out for. It should raise your suspicions anytime you're seeing an experiment where there's a fixed number of trials and you're looking for just there's 2 possible outcomes. Whether it's called success and failure or not, it can actually be a little bit strange to call it success and failure in some cases. Like with heads and tails, which one is success, which one's failure, that's up to you to decide. But that's what we're going to look for to try to identify when we're dealing with the binomial case. Now here we just want to be able to tell whether these examples, whether they're binomial or not, and there's going to be, what are the criteria that are not being satisfied here. If we're drawing a marble from a bag and then recording the color of the marble and putting it back into the bag 10 times, of course it's not binomial because there's not just 2 outcomes. There must be 3 outcomes because you might get 3 different colors of marbles, red, green, or blue, which are in this bag. So that's not binomial. Drawing 10 marbles with replacement and recording how many red marbles, well, that must be a binomial one because it's with replacement. So every time you're putting the marble that you drew back, so the probability is not changing every time. And we're recording how many reds. And so there's 2 outcomes. Either you got a red, either you got red or you did not get red. Those are the 2 different outcomes. And the probability is going to be the same every time. It's going to be like a 1 out of 3 chance to draw red. And so this is binomial. This is not. This is binomial. Drawing 10 marbles without replacement, this should make you think maybe they're not independent trials anymore, because if you draw a red, then the next time to draw a red, the probability changes because there's only 9 reds in there. And so this one already, don't have to read the rest of it. It's definitely not binomial. But here recording how many blues. So it's kind of the same as B, just without replacement this time. Drawing marbles from a bag until a green marble is selected. So it seems like the random variable would be like the number of draws. Number of draws. This one, it's not satisfying the binomial criteria that there needs to be a fixed number of trials, of course. We don't know how long we're going to be drawing until we get a green. But I want to explore, whenever we're carrying on with this binomial, explore this idea of these probability distributions. There's something that we can do in the calculator also to find these values, these 50% values. There's a button in the calculator called binomial PDF. And if we go there, it is in the distributions. If you go second vars, brings up distributions. You have to scroll down a little bit, find binomial PDF. Binomial PDF, you see it takes a number of trials. And what we're doing in this experiment, we had 1 trial. The probability on each trial to get a success. In this case, we're counting the number of heads. So getting a heads, we could call that a success, would be getting heads. The probability to get heads is 50%. And then the x value, what this means in the calculator, what is the x value? This is this data value. And so if we wanted to find this one, then we should put our x value as 0. We're looking to get that many successes, 0 successes. And this should give us, what is the probability to get a heads? Or in this case, it's to not get heads because we got 0 heads. But this one, it's a little bit overkill because you already know what's the probability to get heads. But here I'm just looking at how to use binomial PDF. And also filling out this probability distribution is going to be more complicated if we had an example. What about if we were doing it with 5 flips? I'm going to come over here since I've got some space, going to make a probability distribution. If we did an experiment where we're looking for how many heads did you flip, and what's the probability to get that many heads? On 1 flip, it's already easy. It's just 50-50. What about on 2 flips? It already gets a little bit more complicated. You have to think about what are the possible outcomes. How many heads could you get if you flip twice? And we could do that one. Not to spend too much time on this one. What about your flipping twice? You could possibly get up to 2 heads. You might get no heads because you might flip double tails. You could flip 1 heads, 1 tails. And that would be to get 1 head. So you can think about what is the probability for that. Or what is the probability to flip twice and get both heads? And you might recognize some things about this, or you might actually know these probabilities. of course, the probability to get no heads, that would be out of the 4 different possibilities, you're flipping twice. You might get heads or tails the first time, and then you might get heads or tails the second time. This is just revisiting a few ideas of probabilities in general. If you're gonna do heads twice, you gotta go heads heads, and that's only one of the outcomes. 1 out of 4 chance should be the probability to get double heads, because heads heads is one outcome out of these possible 4. We can also get heads or tails or heads, double tails. 4 possible outcomes, this is called the sample space. If you take one of those possible outcomes of getting double heads, that's 1 out of 4. So we can predict what values are going to be here, but I want to find these values just by using the calculator real quick. I'm going to do the same thing going into binomial PDF. This time there are 2 trials because we flipped a coin twice. Every time it's still 50-50. What is the probability to get no heads? That would be the probability for double tails. We're looking for 25% right here, and that's what we get. And so probability to get both tails, or in other words no heads, is 25%. The probability to get 1 heads, we could just see it if we know about the sample space. Again, this is a simple example, but what about if you did 10 flips? Then I would challenge you to list all the possibilities when you get 10 flips. It's going to take a while, but we can do it so nicely just with the calculator. We've got these commands. We could fill out this table for going up to 10 also just by doing this 10 times and coming up with binomial PDF. And then I want to show you, after this, the point of doing this is to show you what is this binomial CDF. How does that one work? But binomial PDF, this time we want to get 1 heads, so that's our x value is 1. And then we're going to get, it's a 50% chance, that's what we're expecting, 2 out of 4. And then what about binomial PDF again? This time we know it, since it's symmetrical, we could see something about that. We know so many ways what answer we're about to get right now. The probability to get 2 heads, which is also 25%. Now, what if we had a question, what is the probability to get something that would be a range of values, like x is at least, what about we want to get a number of heads at least 1. We're about to flip twice. We want to know what's the probability that we get heads at least once. But you notice at least 1, this could also be written the probability that x is greater than or equal to 1. That's the probability of at least 1. That would be these 2 probabilities together, 0.5 or 0.25, because 1 and 2, those are both at least 1. And so this should be, we would add those together, get 75%. Now, whenever we want to get a range of values, that's the point of that button that goes binomial CDF. The thing is with binomial CDF though, this one, it only works in the case, and I'm sorry for these parentheses, it looks like I'm starting because the binomial CDF also has parentheses here, but I'm going, it has to be in this case where x is less than or equal to something, some value over here. It can only be used in this case. It always means, binomial CDF always means add up the probabilities going from 0 up to the value that you put. So if we wanted to find, similarly, what's the probability that we do not get any more than 1 heads, or the probability that we get 1 or less, we could also say the probability to get at most 1. This would be, see, that would be the probability of getting 0 or the probability of getting 1. The probability of getting at most 1 heads, that would be the language here. At most 1 means either 0 or 1. And so we would be adding those up, 0.25 plus 0.5, that would be these 2 added together, gives 0.75. And to get that value, we would come in here and go binomial, in the distributions, going binomial again, binomial CDF. And there it is. There's going to be 2 trials. The chance of success is 0.5. And this is, what is the maximum value there? When you write it as less than or equals to, what is the number here? Less than or equals to 1. So that's our x value is 1. It's going to add up these binomial PDF calculations going from 0 up until where we told it to stop. And so my calculator is goofing up, but it's going to recover very shortly because we're going to go enter, and it's 0.75. It adds those up from 0 up until where you tell it to stop. And so why don't we see an actual calculation of something. Here we could see one that's a little bit different. We've got 7% of people in the United States have type O negative blood. We take a simple random sample of size 4, and we're going to record the number of people that have that blood type. So if you sample 4 people, maybe none of them have type O negative, maybe 1 or 2 or 3 or up to all of them, which is all 4 of them could have that blood type. And then we'd put the probability to get each one of those. And we would fill in this one by doing just binomial PDF. For example, the probability to get, how about the probability to get none? We can just come in here and go binomial PDF. We have 4 trials because we took 4 simple random sample of 4. The probability of success each time, the probability that you sampled someone with that blood type is 7%. 7% of people have that blood type. And then we're looking for what's the probability that none of them have that blood type. And so I'm going to go back to binomial PDF. We have 4 trials. Probability of success is 7%. We want, what's the probability that none of them have type O negative blood? And it is a 74% chance. It's pretty likely, since there's only a 7% chance that someone has that. If you only pick 4 people, then you can see here it's pretty likely, around 75% of the time, that none of them have that blood type. And we would just do it for all of those ones. What is the probability that no more than 2 people have blood type O negative? And I wonder, I'm actually wanting to explore something to do in the calculator to do this more quickly, to fill out this table just to be able to illustrate. But anyways, why don't we see for part B, what's the probability that 3 people have blood type O negative? There again, we can just go binomial PDF. I don't want to get into too much complicated stuff about how to use the calculator. It's not really part of this video. I want to just see binomial PDF, binomial CDF. If we have 4 trials, 7% chance of success, what about to get 3 people? It seems like it would be very unlikely, huh? And it's around 0.1% chance, 0.001. And then what's the probability that no more than 2 people have blood type O negative? No more than 2. There's the boundary is 2. No more than 2, which means 2 or less. That would be another way of saying 2 or less. Or what about less than or equal to 2? Which less than or equal to 2, that's the thing. We want probability that x is less than or equal to 2. So that would be 0 up through 2. Well, that's convenient because adding up from 0 up to some number, that's accomplished by binomial CDF. So we can just go in there and go second distors, binomial CDF, and then it goes 4 trials, 7% chance that they are type O negative, and we want to go up to 2, but not past 2, 0, 1, or 2. This is going to add up all of those probabilities. If we were to find these, which I did not find them, you know how to find them now. Find these 3. If you add them all up, it's going to give you this number that we're about to get from the calculator, which almost all the time, it's either 0, 1, or 2 people. The 3 and 4, obviously 3 is already super small. Getting all 4 of them have type O negative, it must be even way smaller. The chance that we're going to get 0, 1, or 2 people with type O negative blood is 99.8% of the time. 99, even 0.9%, because it goes 8, 7. Very unlikely. And so here in the notes, I don't want to belabor the point we've seen about adding up these ranges of values. Always CDF goes from 0 up until the stopping point. So you just figure out where the stopping point is. And in the event that we wanted to find, how about more than 2? Like the probability that you find more than 2 people who have type O negative blood. we want to be able to do this calculation using binomial CDF, so we could do, well, this is the opposite of less than or equal to 2, the one that we just found. 2 or less. 2 or less is 0, 1, or 2. More than 2 is the other possibilities, 3 and 4. And that makes up all the possibilities. So we know that this probability and this probability should add up to 1. Or else we can say this is 1 minus the probability that x is less than or equal to 2. And then we already found that one, so we can just come over here and go 1 minus this probability. That'd be the probability to find somebody whose blood type is more than 2. And sometimes it can be more convenient to do this calculation, doing the 1 minus, this is, remember, the complementary events. And so if you have any other questions for chapter 6.2, I hope that I was able to cover a lot of the questions you may have, but I'm always interested in more questions. And so thank you, and I'll catch you in the next video.